Okay, so it gives me a great pleasure to introduce Professor Ady Stern from the Weizmann Institute, who will give the theory review. Professor Stern is well known for his pioneering work on the quantum Hall effect, including the discovery of quantum particles at the quarter of the electron charge. And from the very beginning, he led the theory progress in the field of topological states of matter. It was a personal pleasure to be part of that. Today we'll tell us about the making and breaking of non-abelian states of matter.
Thank you. Thank you very much, Eitan. It's a pleasure to speak at the IPS conference, and it's a pleasure to share the session with Amir, in particular in the presence of our joint advisor, Joe. What I'd like to tell you about, I don't know why this appears here, but I'm not going to try to fight it. Amir, do you have the... So what I'd like to tell you about is some theoretical considerations today on how can we make and how can we break non-abelian states of matter. Now, my plan for the talk is this. First, I'd like to explain a little bit more than Amir did what non-abelian anyons are, why should we care about them, and what they might be good for. Then I'd like to tell you about the two pieces of work that I've been involved in. One is on how we can generate from scratch, if you want, a non-abelian state of matter. And this is work done with Netanel Lidner from the Technion, Erez Berg with my colleague, and Gil Rafael from Caltech. And then what happens to a non-abelian state of matter as we take its dimension and make it narrow and narrow, so that we take it through a transition from 2 dimensions to 1. And this is a work with Ran Sagi, Bert Alperin, and Yuval Oreg, and there's a poster today describing it. So first, what are non-abelian states of matter? Well, non-abelian states of matter are made of a few basic ingredients. First, you need a quantum system. It should live in 2 dimensions. It should have a gapped spectrum. So there's a spectrum of excitations, and there's an energy gap from the ground state to the excited spectrum, and the ground state should be degenerate. But this degeneracy should be very particular. Of course, we know degeneracies in quantum mechanics. Hydrogen atom is the first example we all hear about. But those are degeneracies that come from some local symmetry, in that case rotational symmetry, and are broken when we break the symmetry. The degeneracy we need here is a degeneracy that does not depend on detail. It's a topological degeneracy. What I mean by that is that if you look at the Hamiltonian of a non-abelian state of matter, it would look like that. You diagonalize it, at least in as a thought exercise, you diagonalize it. You get a set of ground states which are all degenerate in energy. Let's call their energy 0, and an excited spectrum that's gapped. Now you come and you perturb your system by any perturbation you want, any local perturbation you want. You introduce coupling to phonons, you shake the system a little bit, you do whatever you want, and what you find is that there are no matrix elements connecting the ground states. The degeneracy of the ground state is not affected. This is basically what defines a non-abelian state of matter. This is what we need to have if we want to have a non-abelian state of matter. Now, everything else changes. there are changes here, there are changes here, and as a consequence, there's a splitting between the degenerate ground states. But the splitting should be exponentially small in something. It's usually exponentially small in some distances, but it should be exponentially small. This is the defining property of a non-abelian state of matter. Now, if all the ground states are degenerate, how do you introduce dynamics into the system? Usually dynamics is introduced by phases that go like the energy differences time. To introduce dynamics into a non-abelian state, what you need to do is you need to change parameters in the Hamiltonian. You need to change adiabatically parameters in the Hamiltonian. The Hamiltonian has many ground states, and as you change the parameters, the ground states change. Now, if you carry out a cyclic change of parameters, you get back at the end. If you do it adiabatically, you get back to a ground state, not necessarily the original one. So, and I hope you can manage the exercise of reading through the Microsoft symbols. But in any case, what it tells you, what's written here behind tells you, is that an interchange of or a cyclic evolution of these parameters corresponds to a unitary transformation that acts within the subspace of ground states. Now, this unitary transformation, it turns out, for non-abelian states of matter, depends only on the topology of the trajectory. So if you change your parameters in some parameter space in a cyclic way that looks like that, or in something that's less stable, but starts and ends at the same point, you get the same final state. So there's some robustness that comes out of topological considerations. Only the topology of the trajectory changes. Now, this is more or less the definition of a non-abelian state of matter. Why is it good? What is it good for? Well, it very strongly correlates with an idea called topological quantum computation, which is an idea of how to create computers in which when you put PowerPoint, this will not appear. Now, this is an idea I will not get into, but if you have non-abelian states of matter and if you can control and manipulate them ably, then you get a topological quantum computation. But on top of that, I'd like to emphasize, this is also a very interesting basic science question. How can you create a system that's so insensitive to details, where ground state degeneracy doesn't split when you change the parameters? Now, we have some examples for that. We have Majorana fermion that Amir discussed a little bit. We have some quantum Hall states, usually going under the name of Reed-Rezai or Moore-Reed ground states, and we have some experimental progress in the attempts to study Majorana fermions. I will not cover any of this just for a lack of time. What I would like to do today is to explain how can we create a topologically protected ground state degeneracy. So I'd like to focus on this issue of a ground state degeneracy that doesn't change as we change parameters. And second, so this will be the first half of the time I have left. Luckily, it doesn't show the clock here. The first half and the second half will be what happens to this protected ground state degeneracy as we remove the protection by making the system narrower and narrower. So the first half, as I said, is done together with Netanel, Erez, and Gil. And there are some related works with less Israeli names, Barkeshli and Chi, Clark, Stengen, and Alishia, Meng, and Vaezi. All of them worked on similar stories. And the starting point is the quantum Hall effect. Now, the starting point of the quantum Hall effect is the classical Hall effect. You know, 2 dimensions, magnetic field, perpendicular to the 2 dimensions, current is flowing, Hall effect, voltage is generated on the 2 perpendicular to the current, and classically we get, as we learned actually as I learned in high school, not too far from here, we get a Hall resistivity that's linear in magnetic field. Quantum mechanically, we get the steps, and the steps are the quantized Hall states. Now, these quantized Hall states have some properties, have many properties, but out of these properties, there are very few that you need to remember if you never heard of them for this talk. One is that this is a system that's gapped in the bulk, like the one Amir was discussing. Second, it's gapped in the bulk, but like the system Amir discussed, it has edge states. But the edge states in the quantum Hall effect are chiral. They move in one direction only. Here on this edge, they move to the right. On this edge, they move to the left. As a consequence of this, the whole conductivity is quantized. And in the case I'd like to talk about, it's quantized to 1/3 of E squared over H. And the last property I'd like to remind you of, and maybe the most spectacular one of this type of quantum Hall effect called the fractional quantum Hall effect, where this quantity is a fraction, is the existence of fractionally charged quasi-particle excitations. What do I mean by that? What do I mean by that for the context of this talk is that if you look at this type of a geometry, where we have an annulus with one edge at the exterior and another edge at the interior, the total charge on each of the two edges is quantized not in units of the electron, but in units of 1/3 of the electron. Of course, the sum of the charge here plus the charge here should be overall an integer. We can't break electrons. But each one of them can be quantized to 1/3 of an electron. The bulk, by the way, is dead. It's gapped. It cannot be changed. So this was a quantum Hall primer, what you need to keep in mind for the rest of what I'd like to talk about. Now, since I talked for like half a minute about the one annulus geometry, I'd like now to look at two annuli, an annulus above another one. So here we have a green annulus and a red annulus, and each one of them is in a magnetic field, a perpendicular magnetic field. But what I'd like to think about is a situation where the density on the upper annulus is equal in magnitude, but opposite in sign to the density in the lower annulus. So these are electrons, these are holes, equal density, equal filling factor of nu equals 1/3, as we said before. And of course, a magnetic field, and just keeping or having graphene in mind, we think about the spin being opposite in the two annuli. So, as a consequence of having a fractional quantum Hall effect in each of the two layers, by the way, I think about the two layers as being isolated from one another with no tunneling in the bulk. So for those of you who know about graphene, double layers and bilayers, this is like a double layer with an insulator in between. So no tunneling in the bulk. Now, so there will be two edge modes. One flowing, clockwise, and the other one flowing counterclockwise at the exterior, and two opposite modes at the interior. Now, what I'd like to, what I'm telling you now is a recipe of creating a non-abelian defect of the Majorana fermion type, but somewhat more, somewhat richer. So I'd like to tell you basically a cooking recipe for creating a non-abelian state of matter from a quantum Hall state. And the reason I'm telling you this is I'd like to focus your attention on the crucial relation between the fractional charge and creating something non-abelian. So what I'd like to do now is to connect, to glue or to stitch the two annuli to one another in such a way that basically I create effectively a torus, right? And those of you who know the quantum Hall field know that a fractional quantum Hall state on a torus has a topologically protected ground state degeneracy. Now the problem is this is a theoretical construct. We cannot create a fractional quantum Hall state on a torus because to create a torus with a magnetic field that points outwards from the surface of the torus, we need monopoles. And we don't have monopoles because our high energy colleagues did not supply us with them. I'm saying that because I see Kobe here. This is kind of a poor man's way of creating a torus. We take two annuli and we stitch them together. Now, what do I mean by stitching together? Just since I'm not going to manage these graphics with the circles. Let's just take this edge and look at it as if it was straight. What we're going to do, the stitching or the gluing process, is to allow for tunneling between the two layers, between the two edge modes. Now, this tunneling, of course, makes the charge on the two modes uncertain, because it allows for electrons to jump from one to the other. Only at the edge. As I said, in the bulk we don't allow it, only at the edge. The total charge is, of course, 0, just for charge neutrality. But here we have a situation where we have basically two metals. This edge state is like a metal, this edge state is like a metal, and we allow tunneling between them. As a consequence, what we get is a wave function that's a sum of many, many values of Q. But there's one thing that cannot be changed by this tunneling process, and this is the fractional part of the charge. Because the tunneling process tunnels electrons. So if we tunnel, if we had a 5 1/3, minus 5 1/3, and we tunnel one electron, we will end up with 4 1/3, minus 4 1/3. I have more examples. The fractional part of the charge is conserved in this process. And we're going to have three different, what's known as topological sectors, but basically three different states with three different values of the fractional part. It can be either 0 or 1/3 or 2/3. Now, the energy does not depend on this fractional charge. And why that? The reason for that is that this wave function will have a very large range of a very large uncertainty in the number of, in the charge. Or if I draw the charge as or the wave function, the probability to find a particular value of the charge, the stronger is the tunneling, the wider spread this wave function will be. And if it spreads over a range of a million electrons, plus or minus 1/3 will not make a difference. And therefore, the energy does not depend on that fractional charge. So we have three different states. They are different, they are orthogonal to one another because they have three different values of the fractional part of the charge, but they are degenerate in energy. The Hamiltonian, this talk is not technical, but the Hamiltonian, if you're interested, has a charging part, which is basically goes like the charge, this Q squared, and the tunneling part, which turns out to go like cosine 6 phi, and the degeneracy can be seen if you remind yourself that the cosine here now has several degenerate minima. So we have three degenerate ground states, and the degeneracy cannot be split unless you change the fractional part of the charge, which means in this annuli geometry, if you want to bring a fractional charge, you need to bring it from the other edge. And if the other edge is very large, it's not going to happen. And therefore, you will have this ground state degeneracy. Now, this gives us a ground state degeneracy, but still doesn't give us non-abelian states of matter, and that's what I'd like to talk about now. Well, here, Amir gave an introduction to what I want to say, and this is the fact that we can gap such edges also by coupling to a superconductor, not just by tunneling, which takes an electron from here and move it to here, but by coupling to a superconductor, which takes an electron from here and an electron from here, forms a Cooper pair and swallow them, or splits a Cooper pair, one electron to each layer. So we now have two ways of gapping the edges, one with a superconductor, in which case, of course, rather than having Q and minus Q, we have a Q and Q. But again, the fractional part doesn't change by splitting or swallowing Cooper pairs. So we can gap by a superconductor, or we can gap by a ferromagnet, which is the tunneling process I described before. It goes under the name of a ferromagnet, mostly for historical reasons. And we're going to have a threefold degeneracy if we have a ferromagnet on the exterior and a ferromagnet on the interior, or again, tunneling and tunneling, or if we have a superconductor at the interior, superconductor at the exterior. But still, that doesn't give us non-abelian states. What will give us non-abelian states is an alternating gapping. If we gap this region by a superconductor, this region by a ferromagnet, or just a tunneling, this region by a superconductor, this region by a ferromagnet, and so on and so forth, what we will have is a situation where there's a ground state degeneracy that scales exponentially with the number of these domino blocks. Okay? This will give us a ground state degeneracy that scales exponentially. And the reason is that now each one of these superconductors, let's say, let me focus on the superconductors, each one of the superconductors can have a fractional charge of its own. And the ground state will be insensitive to the value of that, or the energy will be insensitive to the value of that fractional charge. So altogether, that will give us a degeneracy that scales exponentially with the number of superconductor regions. And I'd like to, and I'll avoid the discussion of when it's 3 and when it's 6. What I'd like to mention is that this degeneracy can be described in terms of zero energy modes, just like the Majorana fermions that exist in quantum spin-Hall effect, zero energy modes which are localized in between, at the interfaces between the superconductor and the ferromagnet. They are known as fractional Majorana operators or power fermions, but in any case, this is what they are. Those are the localized zero energy modes that will take you from one ground state to another. Now, as I said very early in the beginning, I'm going to focus today on ground state degeneracy and not tell you about topological manipulations and unitary transformation and all that, simply because not only that my time is limited, but it's the pre-lunch talk. So I won't tell you much about this, just that you can calculate the unitary transformation that are being implemented when you interchange these zero modes, and you get a set of transformation that's richer than those of Majorana fermions, but are not rich enough to carry out topological quantum computation, or universal topological quantum computation. And I can expand on that, over lunch break if someone's interested. What I'd like to talk about in the remainder of my time is what happens as we try to destroy the state that we just created. So we said there was a recipe of creating a non-abelian state of matter. Just the ingredients of the recipe were 2 annuli, 1 electrons, 1 hole, each one of them in a fraction quantum Hall state, and regions of tunneling and regions of superconductivity. That's all we need. So now what will happen if we take this system and go to the limit, explore what are the limits of after which this topological protection disappears. So this, as I said before, this is a work with Yuval. Eran Sela was involved in an earlier part of this work. I'm mostly going to talk about the second part. Eran Sagin, Bert Halperin, and there's a poster this afternoon or over lunch break, I'm not sure. And what we'd like to examine is this statement that you hear all the time, that anyons live in 2 dimensions. What happens if we make them live in 1 dimension? So for that, I have to introduce a change in my graphics. I don't know how to, I got tired of doing this. So from now on, I'll do my drawings in a top view. So you see these are the 2 layers, the 2 layers, and here are the gapping. This is, what was it, ferromagnet, superconductor, and this is what used to be the annulus. So this closes like that, and it's now a thin annulus. In fact, it's a thin annulus, but it gets even thinner. Here it is now. It's very, very thin. It's almost 1D. do we lose the non-abelian defect that we just talked about creating? The question, I have to say, comes up or is sharpened by the fact that we know that Majorana fermions can live on wires, can live in one-dimensional system with no problem. In fact, they, in some sense, feel more natural in one dimension. So can we get this? Can we get these fractional Majorana fermions to live in one dimension too? The answer is supposed to be no, because there's a theorem that says that it shouldn't be allowed, and this is in two different works by Ady Stern and collaborators. Berg is one of them, and Frank Polman is the other, and Fidkovsky and Kitaev. So if they tell us it's a theorem, let's see how it works. Shalosh? Okay, toda. Let's see how the theorem will work. As always, it's nice to try and break the law and see what happens. So to do that, I get back to my original system. The two annuli fully gapped by only a superconductor in the interior, only a superconductor in the exterior. Basically, this is a Josephson junction. Let's ask what happens to a Josephson junction. So now we are in a somewhat question that belongs maybe to a much simpler world. A Josephson junction where the insulating part is made of an electron hole double layer of a fractional quantum Hall state. So of course, if this thing was very wide, there would be no tunneling from edge to edge, and the fractional part on each of the edges would be conserved. And we talked about that. This fractional part can be 0, 1/3, or 2/3, and it should be opposite here and here because the total number of electrons is an integer. But and the Hamiltonian would look like that because the states are all degenerate. But now, as we make it thinner and thinner, there will be tunneling matrix elements that tunnel charges from the exterior to the interior. And we can calculate the effect of this tunneling matrix element. It basically boils down to diagonalizing a 3x3 matrix. And we are 4 people, so we managed. And what we find is, okay, now, it makes sense to ask the question number 1 that you ask about the Josephson junction. How does the spectrum look as a function of the phase difference between the two superconductors? So here's the energy as a function of phase difference, and it turns out, and here I'm not talking, I'm not yet, I will in my last minute, talk about the question of what happens to non-abelian anyons as we shrink to one dimension and so on. But as a primer to this, what we see, something interesting about this Josephson junction. We see that it has, this Josephson effect is 6-pi periodic rather than 2-pi periodic, and that there are degeneracy points which remain at particular values of the phase difference. Which is to say, we started from a system, the two-dimensional system had topological ground state degeneracy. All the 3 states were all degenerate. Now we allow fractional charges to tunnel from the interior to the exterior. We split this degeneracy, but we do not fully split it. Something is still left behind. Even in the limit of one dimension, something is still left behind. So can we make non-abelian anyons of that? Well, the answer is no, as the theorem tells us. And the way to see that is this. Remember, this black, now I'm coming back to this full-fledged geometry with superconductors and ferromagnet and so on. What turns out, and I won't get into details on that, what turns out to destroy this non-abelian fractionalized Majorana fermions in the limit of one dimension is the fact that even though I can keep them very far away from one another, I can keep the interfaces, the zero modes, very far away from one another and still be in the one-dimensional limit. But superconductors can talk to one another through Josephson tunneling, and this Josephson tunneling turns out to destroy the fractional Majorana fermions and leave us with only Majorana fermions. So in one dimension, indeed, it's only Majorana fermions that whose ground state degeneracy is protected. So to summarize, let me say one sentence about, in some sense, the motivation behind these works. What I really would like to be able to say is to fill this dotted line. What I would like to get to a level of understanding of this issue of non-abelian states of matter, of ground state degeneracies which are topologically protected, to a level of understanding that corresponds, to the level that we understand Bloch bands or band insulators, something like that. So we'd like to know, what does it take for an electronic system to form a fractionalized state or a non-abelian state? We don't even know to say what it takes to form a fractional quantum Hall effect. We just know it's observed in the lab. So this is what I'd like to be able to fill. For the time being, what I told you is how to implant non-abelian defects into an abelian quantum Hall state, and what survives and what doesn't survive in the transition to one dimension. Thank you very much.
Thank you for the talk. Any questions?
Just for curiosity, what happens if you take a disk and act an annulus?
If you take a disk and you stitch it alternatingly, superconductor, ferromagnets, black, yellow, you get a topological ground state degeneracy, you get everything. You cannot go to the 1D limit, because the 1D limit I went by making the annulus thinner and thinner. But other than that, the annulus was needed for the second part of the talk, not for the first. You get the same ground state degeneracy. Yigal?
Topological insulators, you need time versus symmetry. Here, you imagine somehow putting a magnetic field so that it will have an opposite effect in the two layers, but still preserve overall time versus symmetry. Do you have an idea experimentally?
Yeah, no, you don't need to keep time versus symmetry. No way. It's, there's a magnetic field. What takes the place of time versus symmetry here is particle-Hall symmetry, because you have electrons and holes of equal density, basically equal low energy physics. So this is how you compensate for breaking time versus symmetry. In fact, you may know that in graphene, you can see topologically topological insulator physics in like 25 Tesla or something, because of particle-Hall symmetry, basically. What?
Regarding the realization of this system, we talked about graphene, but what about double electron hole,
in let's say, gallium arsenide.
Yeah.
So I should say at some point, and since I didn't say it till now, I'm sure you realized it, but I should say it at some point. This is very difficult experimentally. From the slide with my name and the funding agencies to the slide of the summary, it's all very difficult experimentally. Now, so in gallium arsenide, one of the difficulties is inducing superconductivity. That wasn't, to the best of my knowledge, correct me if I'm wrong, that was never done. Right. But, we'll do it, and then we can.
Okay, so.
Thank you very much. מי זה שלך?